Hey, Joel, I'm going to try to do this fairly quickly. I'm not sure if I can get to it. I get a little talkative when I'm trying to explain things, but I'll do my best. First of all, as far as this top box, I've tried to eliminate, put an X next to things you won't need, and maybe just in case they ask you questions about the kinetic energy of a proton, a neutron, or etc. I don't think you'll need it, but I'm putting that anywhere anyways. Again, X is thereabouts the electrical unit, and actually hertz you won't even need also. So your instincts are right. Trig function or trig, those common triangles. Good to know. It's like an ACT. Sometimes they pull those out. I don't, like force is going to be applied at 30 degrees, right? So you could be able to calculate the components of the force pretty easily. Or it could be at 37, or it could be at 45, something like that. So they like their common triangles. I circled the 1, 2, and 3 on the conventions. Basically, this inertial frame of reference, if there's a net force, you've got acceleration. If there is no net force, you don't have acceleration. Note the air resistance assumption, and then work is positive. So that pendulum example I have in the classroom, if I apply work over or force over distance, which is work, I'm adding energy to the system. That's positive, right? And if the bowling ball does work on a box, a force over a distance, it's negative. It's taking energy out. So you highlighted the force of friction. One, this is intended to get static friction and kinetic friction all in one equation, meaning less than or equal to. So that peak static friction before it releases and then it goes to kinetic. But I think it's usually about what the heck is the absolute value sign there for. Force is a magnitude and direction. They are trying to use absolute value symbols to indicate magnitude only. Okay. I did not emphasize centripetal acceleration, A sub c. I just put it in the equation that we discovered with our circular motion. The net force or net centripetal force is mass times the centripetal acceleration, and centripetal acceleration is v squared over r. Delta p is force times delta t. That is the impulse equation from chapter 7. So I apply a force for a period of time, and I change the momentum of the object. So I apply a force with a baseball bat to a baseball, and it changes the baseball's momentum. Okay. There's a lot of examples for that, but I hope that helps clarify it. The P equals delta E over delta T. Power is the rate at which you use energy. So if I were to say change in kinetic energy over time, how much power do I need to accelerate that, right? Change in velocity. And then also how much power do we need to lift a certain thing, a certain height? That's a change in energy also. So that's that. As far as this x equals a cosine theta, clearly not an algebraic expression, so I don't expect you to use the algebraic expression. But what I do expect is the understanding. It looks like a cosine curve as far as harmonic motion goes to a peak, goes to a trough. You can kind of visualize it with a spring. You can extend it to a pendulum. They're going to ask you about, like our last assessment was on for harmonic motion. Where's the max kinetic energy? Where's the minimum kinetic energy? Where's the max potential energy, etc.? If I look at that position time curve, which looks like a cosine wave, if I look at the slope, which is velocity on a position time curve, at the peaks, I have zero velocity. It's horizontal. So my peaks here. So I know I have minimum kinetic energy. And then when it's passing through its equilibrium point, right, at zero, right, that's where I've got the maximum speed, okay? Now over here, I want to just talk about positions 1, 2, 3 on a hanging mass. Specifically, that was on our assessment. At equilibrium, if it's passing through equilibrium, right, we know from our chart or our graph that it's zero potential energy, but maximum speed. But in position 2, I've got two types of potential energy. I've got spring potential energy because it's compressed, and I've got gravitational potential energy because it's up higher than, say, equilibrium point, okay? And so I've got two restorative forces at the top, meaning I've got more potential energy or max potential energy there. When I'm in position 3, what kind of restorative forces do I have? I've got potential energy spring, but my gravitational is a negative restorative force. It's helping it keep it down. So I don't have zero potential energy. I don't have maximum potential energy, you would think, at an extreme. But this vertical spring, it's neither, essentially. Okay. Let me talk about, while I'm on the screen, let me talk about this torque equals R force sine theta. I hate that they put sine theta in, because it depends on where your theta is. Okay, where I have my theta written, it's actually, right, this force perpendicular. Similar to work, you wanted to find the effective force that's causing the work, so the force that's in line with the displacement. Well, when I'm working with torque, I want to find the effective torque, right, or the effective force that's causing rotation, because otherwise, if I have force that's parallel, it's going through the axis of rotation, which is not causing rotation. My perpendicular force is the one causing rotation. So it's this force at this radius. Those have to be perpendicular to one another to get the effective force. And so that is on, where is that equation? Oh, right down here. Whoops. I don't have my pencil. Right down here. As far as RF sine theta. So that sine theta makes me nervous. I hate that thing. Because is it accurate? Well, it depends on where your theta is. This delta L, I'm going to picture visualize The Price is Right. Have you seen that? I hope you've seen it. A guy stands up at this big wheel. He grabs up high and he applies a force, right, downward. Now, you could call that a force a torque because it's a force at a radius, and then he applies it for a certain amount of time. And that causes a change in angular momentum, or delta L. Okay, so if we look at L right above it in green, rotational inertia times omega, which is that rotational velocity, you're going to have a change in rotational velocity when you spin the wheel. You apply a torque over a time. I think on your force spring, again, that's magnitude only, not direction. And think about that. In AP, they use an ideal spring instead of a one-dimensional spring, meaning I can compress the spring, right? Or ours, we usually hung a spring. They could stretch, but they couldn't be compressed. They have an ideal spring that can be compressed and extended. And it's essentially saying if I compress it a certain X value, so if I compress it 2 centimeters, I get a certain force. They say if I extend it 2 centimeters, I get that same force, but they'll be in opposite directions, right? So that's why it's magnitude only. Period equals 2 pi over omega. Just something to reference. If they gave you angular speed, you can find that period. I didn't emphasize it in rotation at all. You could correlate it with our circular motion, where omega equals linear velocity, translational velocity over radius. And then you'd go back to our circular motion lab, but this is really rotation. So let me go to this force of gravity. That's using that universal gravitational constant. And again, I think it's all about the absolute value symbol. It's all about magnitude, and then you determine the direction. So let's see if I can go to this use of G. And again, use of G should be related to potential energy, gravitational. And real quick, electricity and waves are out. So while I go away, this is going to be my last comment, where that equation comes from. We did not touch on it in class, but it's there for you, and hopefully we can go through this process of where it came from. Okay. So if we're going to do 2 different ways to find the force of gravity, I could use mg if I knew I was on Earth, or I could use a universal gravitational constant, my mass, 1, the mass of the Earth, and the radius between the two. Okay. Now I can eliminate mass 1 on both sides and get g, little g, big G, mass of the planet, or radius of the planet. That would be the gravitational pull of the planet. Now, my normal potential energy gravity is mgh. But if I substitute for my mass, what's my potential energy for my mass? A satellite in the air, right? Well, what's the g? Well, the g is universal gravitational constant mass of the planet over the radius between the satellite and the planet. And then what's the height? Well, the radius between that and the planet. And what will happen is the r squared and the r will have a little bit of cancellation, and you will end up with that equation. If I want to find the potential energy of, say, a satellite in space, right? It's moving, it's got kinetic energy, but it also has potential energy. The mass of the satellite times the mass of the planet times the universal gravitational constant divided by r will give you your potential energy for using the universal gravitational constant. It's really just a redefinition of mgh, but on a big scale. Okay, I hope that helped. That was fast. Please let me know if you have questions, and I am going to pull out of this. Maybe.